And welcome back to part B of OSPF in a single area configuration. So this is the second half of module 2 or chapter 2, and what we are going to continue with is modifying our area, our default route propagation through OSPF, and verifying that our OSPF implementation is working. So we need to be able to adjust the cost of each link within OSPF. So the metric that it uses is a reference bandwidth divided by the interface bandwidth, and this allows it to form a number. This number is the cost of using the link. The lower the cost, the better the path. And what occurs is technology improves over time, and we have seen the cost become superseded. So when this was first developed, it was developed with Ethernet, which was slow. Now we have gigabit and 10 gig Ethernet interfaces out there, and the original formula would have multiple cost ones because we can't go below one. Okay, we don't have any, it has to be an insurance, a full number. So anything that would equate to a value less than 1, as in 0.5 or 0.4, the cost is 1. So we need to be able to manually adjust the cost, and we can do that on setting the cost on each interface with the IP OSPF cost command if we wanted to do it that way. The better practice is to use the auto cost reference bandwidth command to actually change the reference bandwidth value, and we do this on all the devices. So if we're going to use the auto cost command, it's best practice to change that value on all active devices within our area. That way the cost calculations will be the same across all devices, giving you a better view of the entire topology and more accurate cost calculations as you go through. So if you look at how this works, it was designed with Ethernet in place. So you do the calculations. Ethernet 10 megabits is 1, fast Ethernet is 1, gigabit Ethernet is 0.1, so it's 1. 10 gigabit Ethernet is 0.01, which rounds off to 1. So you can see how this cost calculation is not going to be reflecting the true best path between these different levels of bandwidth. So we need to adjust that cost path. Okay, so historically you can see where the values came and the problem occurs with the newer technologies being implemented. So we need to adjust this. And the way we adjust this is with the auto cost reference bandwidth configuration command. Now this command uses megabits per second. So for a base reference number. If you want it as gigabit, the gigabit is 1000 megabits per second. If you want that reference to be for 10 gigabit Ethernet, then it'll be 10,000. Okay, so you want to be able to go in there and put this in as part of your routine when you're setting up OSPF. Look at your topology, look at what your links are. Let's face it, most of our networks now are based on 100 1 gig ports. Some of the newer installations, especially when you're dealing with fiber, have 10 gig all over the place. So you need to make the adjustments here. Or you can manually go through and set up your OSPF cost. Now the cost is only applied to the calculations as the packets are received. So when that hello packet comes in, the cost value represented in that packet is added to the local cost of the link, and that's what the calculation is based on. So what we end up with, if we've set that new reference point using the 10 gig reference, is a new cost chart, which actually represents the relative cost per interface type throughout the network. So our 10 megabits per second interface is now costing 1,000 to use, whereas our gigabit interface is costing 10. So we have the relevant costs and differences in performance that using those links, so the path, would actually cost the protocol to use. It can now make decisions based on the true costs of the links and choose the most efficient path to get to its destination. So as I said, we need to use the command on all devices participating within our network, and that way we can get the costs represented correctly in our routing table, and it can choose the correct path. So knowing the costs, what we can do is then work out the path. Okay, so in the example here, it is using total cost for router 1 to reach the 10.10.2 network, which is this one here on router 1. So router 2, so we're trying to look at router 1 getting to router 2's loopback 0. So when router 2 advertises the existence of this network, it has a cost of 1. So when that cost or the hello packet is being sent along here saying, I have this network, the cost is 1. As it arrives on the G00 network, it knows the cost of using this link on this interface is 10, and the advertised cost from router 2 to get to this network is 1. Adds them together, so it knows it's a cost of 11 to get to this network. Now, it'll also get an advertisement via router 3 saying it too can get to this same network, but it'll do the same calculation as it arrives on G001, and then when router 3 sends that same information saying this network's available via me, it adds another 10. So the cost to get to 10.10.2 network via router 3 is now going to be 21 compared to a direct path between router 1 and router 2 of 11. So you can see how advertising the correct cost is important to determining which path to use. If we didn't change the reference, all the cost values would still occur. This would be 1, this would be 1, and you would still have a difference because you'd have a cost value of 2 and 3. So it still increments, but when you get into faster speeds, it's not reflecting the true available bandwidth and the capacity of those links correctly. So it's very important that we get those costings right so that the devices can determine the best path with the highest available bandwidth to get to our destination. So if we look within our routing table, we now have our route displayed with a metric value. The metric is the cost of getting to that destination network. And it's a very simple calculation. The lower the metric value, the better the path. Okay, so just as a reminder, the first number in here is our administrative distance. In other words, how trustworthy our protocol is, the method that this destination route was learned, as the protocols use different methods of calculating its metric from each other. So we need to determine which protocols we trust over others. In other words, is OSPF better than RIP, for example? Yes. So it has a lower administrative distance. So it will be used over RIP, for example. RIP's 120. Then once we have determined the paths and which protocol is trusted the most, then if there's multiple advertisements for the same network, it'll look to see which is the best metric and then inject or use that best path in its routing table. Just as a refresher, you should all know this by heart by this stage, but just as a refresher. Now, by default, a loopback interface will have a cost of 1. So if we want to influence that, for example, and this graphic is so messed up, it really needs, okay, that should be on separate lines. They forgot to recalibrate it when they made these slides up. Unfortunately, it's a graphic. I can't actually change it unless I do the whole thing from scratch again. So we go to the interface, we type in IP OSPF cost, and we're changing the cost to 30. So when we have routes received on G001, they will now have 30 added to the cost for determining the route. Routes received via loopback 0 will now have a cost of 10. Added to them, or as they are advertised to our neighbours, these costs will be the ones advertised. So when we look at the cost of getting to our various locations, you'll see the metric values change. Now, the changeover will occur if the timers time out. So a entry in the routing table is only there for a set amount of time. If a link goes down, an update to the status is sent out and new paths are determined based on that new information. So router 1 is learning all of these subnets are available via this neighbor, okay, which is router 3. So if router 1 can no longer use its primary route to get to 10.114, it knows it can get to it via router 3, but with a much higher cost. So this is a backup. So remember, hello packets are sent basically every 10 seconds. And the dead interval is 4 times that, so 40 seconds. Now, if we don't have receipt of those packets, the neighbor relationship is removed. And this will affect all the link states in the device's database, and it will recalculate all the pathing after removing all of those entries, because they are now considered invalid because their source no longer exists. So where to look for the timers? Within the OSPF interface, it will tell you what the configured timer on that interface is. Now, each device needs to agree on the area and the timers. Okay. If these don't match the device is sharing information, well, they won't share information. They won't form a neighbor relationship. So when you look at the neighbor output, you see the dead time. It's counting down. You can see here that it should receive another update from neighbor 2222 in the next second. And if it receives that hello packet, it should start the countdown again from 40, counting down. So you can see straight away whether it has received its hello packets from the neighbors by looking at the dead time. If you're in the 20s or the 10s, you know that something's going wrong with communication because it's counted down below 30. That means it's missed a timer. Okay, it's missed a hello packet. There are legitimate reasons why a hello packet won't get there, because it's using the same bandwidth as legitimate traffic. So if there's overwhelming congestion, your timers will go past that. It's unusual, but it can occur. So we can change the timers. If you're going to change them manually, you need to go through and do it through all the devices. because remember, they've got to be the same or else the neighbor relationship doesn't form. So to do that, we use two commands, IP OSPF hello interval and IP OSPF dead interval, and the seconds after that. Now, reminder, dead interval is 4 times the hello interval. Okay? If you change these things, you are changing the way the protocol works within your network. Only do this if you have a very valid reason to. Okay? It will change the behavior of your network and can create a very unstable network by making changes to these values. Just a bit of a warning there. To revert them, use the no command version, so no IP OSPF hello interval, and that reverts them back to the default values. Now, as I said, should be 4 times. The problem with this is you're going to have things drop out until you get to the other neighbors and change their timers. Your exchange will go down because the timer is now not the same and they need to be the same for all of the participating devices within the same environment. So when we're looking at a point-to-point, timers have to be the same when we're between the two devices. When we're talking a broadcast environment, we need to have it set so all the devices within that broadcast environment are all using the same devices. So you can see changing it can become problematic on large complex networks. So as I said, make sure you've got a very good reason for changing the timers and realize the impact that it will have on your network. Default route propagation. So we want to be able to find the internet. That's the most common reason we have a default route. So it's not part of our network, send it out this gateway. So the gateway, static default route, IP route, quad 0, and then the next hop address. Now, this only will be known to the local device. So you'd have to go through and configure this on every device. Now, that's a bit of a pain, isn't it? So by using the default information originate on the router that has that gateway, that will propagate it. So, alright, so in this example below, we've configured loopback interface 1 as our de facto internet connection, and we've created a static route pointing to the loopback interface with our quad 0. And when we go into the routing process and say default information originate, and that will inject that default route into the updates, and everybody will learn to send information to this default gateway via the routing updates. Now, one little issue with this. It doesn't update the cost as it goes through. All your costs to the gateway will be the same. Just a word of warning. Alright, so on router 2 we will have a static and it's directly connected, whereas on our other devices it will show up as a static, so the asterisk representing that it's a candidate for a default gateway. And in OSPF, anything that is injected is an external route. So as this is being injected into the routing updates from an external source, it becomes an E2, which just means it's learnt as an injected source. The E1, E2 and the differences of how they're handled within the OSPF protocol is in the advanced OSPF chapters, which is part of the CCNP course. But basically what it's doing is it's taking that static route that is only valid on router 2, injecting it into the OSPF protocol to be distributed within link state updates to all of its connected networks. And all the other devices will learn that a default gateway exists and to send packets destined to that device. Let's make sure everything's working. So show IP interface brief, should be all familiar with that one. Show IP route, should be all familiar with that one by now. So these are making sure OSPF entries appear within our routing table and that our interfaces are active with and correct IP addressing. Now, the one thing that the interface brief command does not show us is the subnet masks. Okay, so just be aware of that. I've seen so many people just do show brief, and go, yeah, it's configured correctly, move on. But because it's not showing you the subnet of that interface, you're not going to see any typos that are in the configuration for the subnet information. Just be aware of that. If your interface is up and you still can't get the right connection, actually look at the IP interface, not the brief, the specific interface that you're having trouble with. You might find a typo in the subnet mask. Next is the actual OSPF commands themselves. So there's show IP protocols, show IP OSPF, show IP OSPF interface, and show IP OSPF neighbor. Now, be aware, which I'm sure you all are now, the English for these commands are based on American English, so they don't have the U where we would normally expect it for our more traditional English people. Neighbour has a U for us in Australia, in the UK, New Zealand, under normal English communication. Not so from the source of the operating system. So just keep in mind to override that natural instinct to put in the U in those commands. So what does our show IP OSPF neighbor command give us? Gives us the status of all of our neighbors. They will tell us whether the state's full, dead timer, what the IP address is, and which interface is used to communicate to them. Now, reasons why neighbours will not form. Subnet masks don't match, so therefore they're not on the same network. The hello timers and dead timers do not match, so they will not talk to each other. We have a difference in network type, so point-to-point and broadcast, they are not compatible with each other. And you're missing some of the commands. So if you've decided to use the network command under the OSPF routing, you may have made a mistake in the wildcard mask. That will affect whether the interface is participating or not. So just go through and check your commands depending on which one you use, the network command under the routing process or the interfaces joining the process. Under protocols, you will get a list of all protocols that are running on the device, not just OSPF, but you would get a section on OSPF. This will tell you what the process ID is for the device, what its router ID is, what areas are active and the interfaces that are participating in the area, and what neighbours it's sharing information with, and what the default administrative distance for this protocol on this device is. If I specifically want to look just at OSPF, using the show IP OSPF, it gives me different information. It tells me the OSPF process number, its ID, how long it's been up, but then it'll tell me different information regarding OSPF itself. So it tells you what the bandwidth reference value is, and then it'll tell you what area it's attached to. It'll tell you how many times it's recalculated the algorithm for path calculations, number of link state advertisements it's sent and received, and a little bit of extra information. So if you look at the interfaces under Show IP OSPF interface and specify which interface you want to look at, this is where we find the network type and the cost for that link and how many adjacent devices are available via that link. So as there's a point-to-point network type, you would only expect to see one neighbor. If it's broadcast, you would expect probably to see more than one neighbor. So on the Show IP OSPF interface brief, this will tell you which interfaces are participating within the process. It'll tell you what the network address that is being advertised, the costs of each link, whether it's point-to-point or broadcast, so the network state, and it'll also give you a count of the neighbours in each area. Sorry, each link, not area. Let's get the terminology right. You'll notice that the loopback is 0, 0 because it's talking to itself, so it doesn't expect to see a neighbour. The other ones you'll see there, so you'll have the active and total. So if it was a broadcast state and one of them had timed out or gone offline for whatever reason, you would possibly see one of two, something like that. So it'll tell you, hey, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, the difference between the full and connected, so it tells you if there's anything problematic in its communication. So for those that are actively doing the course, it would now be time for you to go off and do your module practice and quiz questions, do your labs. Alright, so in summary, what did we discuss over Part A and Part B? So we know that we can enable the process with the router OSPF and the process ID, and that process ID is a value between 1 and 65,000. The router ID is a 32-bit value that's represented in dotted decimal format, and we know that we have an election process that occurs on different types of networks. But before we get there, we need to know how the router ID is chosen, and we can manually configure it with the router ID command. That would be the first choice. The second choice is the highest IP address on a loopback interface. The third choice is the highest active IP address on a physical interface. We looked at the fact that we can join networks to the routing process two ways. We can use the network command under the routing process using the network statement, wildcard mask, and area ID, or we can go to the actual interface itself and join the interface to the process using the IP OSPF interface command. So with this, we join the interface to the process using IP OSPF process ID, area ID. So in the examples we used, that would have been IP OSPF 10, area 0. Passive interface is configured under the routing configuration, and this disables the hello protocols being sent out of that interface. Now this allows you to advertise the network to other devices, but not to have it actively participating out of that interface. Good reason to do this would be on networks that only have host devices connected to them, so they do not need to see traffic from a routing protocol. The election process takes place wherever there is a broadcast network, so multiple access, and the election process defines who is the designated and backup designated routers, and by default it will use the highest router ID to determine that. Now that is not necessarily the best way of doing it. You may want to change the priority value on the link to influence the election. Okay, so the higher the priority value, the more likely that device is to become the DR. The DR is responsible for collecting and distributing all link state advertisements, which are the changes within the network. It uses the multicast address 224.0.0.5 to communicate to all the other routers. If for some reason it no longer is sending updates, the backup will become active and take over that role. Now, all the other devices will send their change notifications, the LSAs, to the DR and BDR on multicast address 224.0.0.6, and now we get into the verification commands. So the show IP OSPF interface, OSPF neighbor, so checking to make sure that the states are what we would expect. And then here we have the discussion about changing priority values to influence the election. That should, I might have to change that in the presentation so it sort of flows on likely with the presentation material, not out of sequence like it is now. Cost reference. So remember, we need to change the reference bandwidth on all the devices so that it will correctly allocate link costs based on the newer technologies. So the higher the bandwidth interfaces are proportionally representative in the costing and not all ending up with the same value. We talked about the fact that we could manually set the costs on each interface if we wanted to, using the IP OSPF cost followed by the value. We talked about the fact that we can change the interval timers, how long it waits for the lack of hello packets to arrive before it considers the link dead. So you change the hello interval, and the dead interval should always be 4 times the hello interval. And then we had a look at how we could propagate a default static route throughout the process, so everybody knows where the default gateway is. And then lastly, we went through the various show commands to verify the operation of process. And that brings us to the conclusion of part B and the chapter. Hope you have found this informative, and I'll catch you in chapter 3.